In 1965, the United States launched a nuclear reactor into orbit. It worked for 43 days, then it failed, and nobody tried again. That reactor is still circling Earth right now, leaking debris, and it will keep orbiting for another 3,000 years. For 6 decades, no American spacecraft has carried a working fission reactor. That's about to change, and the story of why it took 60 years is more disturbing than the reactor itself. NASA just announced it will launch a spacecraft called SR-1 Freedom, Space Reactor 1, before the end of 2028. It will carry a nuclear fission reactor, use it to power an electric propulsion system, and fly that system all the way to Mars. When it arrives, it will deploy a fleet of small helicopters onto the Martian surface. This isn't a concept, it isn't a study. NASA has committed to building and launching it within 2 years, and here's the part that makes no sense. Just months before this announcement, the United States government killed its own nuclear propulsion program, canceled it, zeroed the budget, said it was too expensive and too slow. The program was called DRACO, and it had been running since 2020, with $500 million in contracts, partnerships between NASA and DARPA, and hardware being built by Lockheed Martin. Then in mid-2025, it was dead. So how do you go from canceling nuclear propulsion to announcing a nuclear spacecraft in under a year? The answer involves a 60-year failure, a bureaucratic reversal, and a space race that America is terrified of losing. Let's go back to 1965. The Cold War was at full intensity. The Soviet Union had already launched more than a dozen nuclear reactors into space, most of them powering radar satellites that tracked US Navy ships from orbit. America's response was SNAP-10A, a compact fission reactor small enough to fit inside a satellite. It launched from Vandenberg Air Force Base on April 3, 1965, settled into a polar orbit at 800 miles altitude, and powered up. For 43 days, it ran perfectly, producing over 500 watts of electricity from controlled nuclear fission. Then a voltage regulator on the satellite, not the reactor, failed. The reactor shut down automatically. Nobody went up to fix it. That was the last time the United States operated a nuclear reactor in space. Think about what happened in those 60 years. We landed on the moon. We built the space shuttle. We constructed a space station the size of a football field. We sent rovers to Mars, probes to Pluto, and telescopes to the edge of the observable universe. But we never launched another nuclear reactor, not once. It wasn't because the technology didn't work. It was because the politics didn't. Every time a nuclear space program gained momentum, something stopped it. Project Nerva tested nuclear thermal engines on the ground in the 1960s and early 70s. They worked beautifully. Engineers fired them up in the Nevada desert, ran them at full power, and proved they could generate twice the efficiency of chemical rockets. Then Nixon slashed the space budget, and Nerva was canceled. Project Prometheus aimed to send a nuclear-powered probe to Jupiter's icy moons in the 2000s. Cost estimates spiraled, and Congress killed it after spending over $1 billion on studies. DRACO, the most recent attempt, made it further than any program since Nerva. Lockheed Martin was building the vehicle. General Atomics designed the reactor. DARPA and NASA were co-funding it with $500 million. Then in May 2025, the budget request came through with $0 for nuclear propulsion. The official reason was blunt: too costly, too slow, and SpaceX's falling launch prices made chemical rockets good enough. But here's where the story takes a sharp turn. Less than a year later, in March 2026, NASA Administrator Jared Isaacman stood at agency headquarters and announced the most ambitious nuclear space program since the Cold War. Not nuclear thermal propulsion like DRACO, nuclear electric propulsion. A different technology. Same radioactive core, completely different application. The distinction matters. DRACO would have used a nuclear reactor to heat hydrogen and blasted out a nozzle. Essentially a nuclear-powered rocket engine. SR-1 Freedom uses a reactor to generate electricity, which then powers ion thrusters that accelerate tiny amounts of xenon gas to enormous speeds. It's slower off the line, but dramatically more efficient over long distances. Think of it as the difference between a drag racer and a diesel freight train. One is fast in a straight line. The other can haul cargo across a continent on a single tank, and hauling cargo is exactly what NASA needs. The agency's new plan isn't just to visit Mars. It's to build a permanent base on the moon first, then use nuclear-powered transport to move heavy equipment between Earth, the moon, and Mars. SR-1 Freedom is the proof of concept. If it works, it changes the economics of everything beyond low Earth orbit. But the nuclear reactor aboard SR-1 Freedom isn't just a propulsion system, it's a survival tool. On the moon, nights last 14 Earth days. No sunlight means no solar power. Without a nuclear reactor, any lunar base goes dark for 2 weeks every month. Batteries can't cover that. The reactor NASA wants to deploy on the moon by 2030 would provide 20 kilowatts of continuous power, enough to keep habitats warm, water recyclers running, and communications alive through the long lunar night. And this is where the geopolitical pressure becomes impossible to ignore. China isn't just planning to land astronauts on the moon by 2030. China and Russia have a joint agreement to build their own lunar base, powered by their own nuclear reactor. The country that masters nuclear power in space first will have a permanent strategic advantage. America knows this. It's one reason the political winds shifted so fast from killing DRACO to launching SR-1 Freedom. There's another reason, and it's darker. Right now, above your head, the original SNAP-10A reactor from 1965 is still orbiting at 800 miles altitude. In 1979, 14 years after it died, it started shedding debris. 50 traceable pieces broke off over 6 years. The cause was never confirmed, but a collision with space junk is suspected. Whether radioactive material was released remains unknown. NASA estimates it will stay in orbit for another 3,000 years. A dead nuclear reactor slowly disintegrating, circling the planet that built it, and forgot about it. Meanwhile, the Soviet Union didn't share America's hesitation. Between the 1960s and 1980s, they launched over 30 nuclear reactors into space, most of them powering radar ocean surveillance satellites. When one of those reactors, Cosmos 954, crashed into northern Canada in 1978, it scattered radioactive debris across 100,000 square kilometers of wilderness. The cleanup cost millions. The Soviets paid Canada $3 million in damages and kept launching nuclear satellites. SR-1 Freedom is designed to avoid that legacy. It will fly to Mars, not orbit Earth. Its reactor is engineered for deep space, far from populated orbits. But the fundamental question remains the same one that's haunted nuclear space programs since the 1960s. What happens if something goes wrong during launch? A rocket carrying a nuclear reactor explodes on the pad. What then? This is the question that killed every program for 60 years. Not the engineering, the fear. NASA's answer this time is straightforward. The reactor won't be activated until it's safely in deep space, far from Earth. Before activation, the uranium fuel is less radioactive than the natural uranium ore sitting in mines across Colorado and Wyoming. The real risk window is narrow, the first few minutes of launch. And during that window, the reactor is essentially inert. Whether the public accepts that explanation will determine whether nuclear propulsion finally breaks through or gets killed again for another generation. Here's the bigger picture. NASA's entire Moon-to-Mars architecture now depends on nuclear power working in space. The agency committed $20 billion over 7 years to build a permanent lunar base. They paused the Gateway Orbital Station, an international project that Europe, Japan, and Canada had invested billions in, to redirect resources towards surface infrastructure. That infrastructure requires power. Solar panels alone can't provide it. Nuclear is the only technology that can. If SR-1 Freedom fails, the timeline slips. If it succeeds, it opens a door that's been locked since 1965. Nuclear electric propulsion could eventually cut Mars transit times dramatically, enable missions to Jupiter and Saturn that solar-powered probes can only dream of, and provide the energy backbone for permanent human settlements beyond Earth. The United States launched its first and only space reactor 61 years ago. It worked for 6 weeks. Then America walked away and never went back. In that time, the Soviets launched more than 30 nuclear reactors into orbit. China is building one now. SR-1 Freedom isn't just a spacecraft. It's a 60-year overdue answer to a question America has been afraid to ask. Can we trust ourselves to put nuclear power in space? By 2029, we'll know. If you were alive in 1965 when SNAP-10A launched, chances are you never heard about it. If you remember the Challenger disaster, you understand why nuclear rockets terrify people. But here's the question that matters now. Do you trust NASA to get this right? Or should we leave nuclear power on the ground where we can control it? This is one of the biggest engineering gambles of the century. And your answer might depend on how much you trust the people making the call.